Good afternoon, or morning, good morning, and welcome back. Um, we're in chapter 5. We're done with kinematics and the description of motion. Now we're trying to start learning about what causes motion. So this is a big day. And uh, what causes motion, meaning you have an object, or what causes the change in motion, I should say, uh, will be the force. So this is chapter 5. So chapters 5, 6, 7, and 8, they're devoted to Newton's laws. In fact, chapter 5 starts to introduce what are forces. Chapter 6, we will apply Newton's second law. And then chapter 7 is devoted to just Newton's third law alone. And so more applications. And then chapter 8 will be motion in I believe it's motion in 2 dimensions. So it's still Newton's laws, but in 2 dimensions. You get circular motion and so on. So this chapter is mainly descriptive. Chapter 6, we will use numbers, in fact, too. So this is mainly qualitative here. So first of all, a force, we will be more rigorous with this, but let's take it qualitatively now. As a force is a push or a pull on an object. So you know when you experience a force. So somebody maybe pulls you or somebody pushes you. Or you know when you apply the force. I can lean against the wall or the board here. Or I can maybe try to pull the board. It's a push or a pull. A push away, a pull would be toward. There are 2 types of forces. Here's a typo, 2. 2 types of forces. The forces can be contact forces, meaning the 2 things have to touch. So I cannot apply a force to the board from far away. I can wave to it, I can do whatever, but the board is not going to feel a force. So if I want to lift the board, I have to be in contact with it. So I have to interact with it. I have to be in contact. Those are called contact forces. And there are long-range forces where the interaction happens from a distance. So for example, the sun's pull on Earth. The Earth and the sun, they're not connected by a hidden string, or they're not connected by a rope or anything. Or, for example, this piece of chalk, if I leave it, it will drop. The Earth will attract it. The Earth will pull down on the piece of chalk, and it will fall. So the Earth's force, or the force of gravity, is a long-range force. It happens from a distance. This semester, basically all the forces we will have, they are contact forces. If 2 objects are not touching, then they cannot apply a force to each other, except for the force of gravity. Okay. Next semester, there are other forces like the magnetic force and the electric force. They are long range. So, for example, a positive charge here and a negative charge here, they will attract one another even though they're not connected, they're not touching. So those are long range forces. So in general, they break down this way. So what are some common forces that we encounter in this class? So here are some common forces, and I'll tell you whether they are long range, short range, long range or contact, and what the symbol is for them. So common forces. Oh, you got the force of gravity. So let me write white chalk here. The gravitational force, let me just pull it down here, because the symbols are not universal. So you got the gravitational force. And it is given the symbol Fg. Okay, Fg, that's the symbol for it. By the way, forces are vectors, and when you have multiple forces, sorry, I forget to say that. When you have multiple forces on an object, it turns out that the net force, the net effect will be the sum of the forces, and you add them the way you add vectors. We learned how to add vectors, and we will talk about it when we deal with them. So that's the force of gravity, and it is long range. So it's the force of gravity, it's long range, meaning it's not a contact force. It can act from far away. We will deal with spring forces. I'll show you a spring in a moment. Spring forces. The symbol for a spring force is F spring, SP. That's the symbol our book uses. The spring force, and it is, it can, so by the way, the gravitational force is always attractive. The earth always pulls you down. It never propels you. It never repels you. So it's attractive. Let me just put it here. Attractive. Always attractive. Attractive. The spring force is a contact force. You have to be in contact with the spring. So it's contact. It actually can either attract or repel. It can be attractive as well as repulsive. Here is a model of a spring. Here's a spring. The spring will be here. It's connected to a wall. And here is a spring. Here is a spring. So you cannot stretch the spring by just pulling on one side. You have to anchor it from one end. So that's where we anchor it here to the wall. And then you can stretch it. Then you can pull on it. Okay? You can pull on it. Some springs you can also push on them, but this one is, you can't really push on it. You cannot, because the windings, they're in contact with one another. But springs, usually, in general, you can either compress them or you can pull them. An example of a spring that you can compress is the shocks in your car. So when you sit in your car, the springs compress, and so they try to push you up. Because you're trying to push them down, they will push you up. And if you try to stretch them, then they will try to pull you down. So this spring here, when I try to pull on it this way, the spring itself is pulling my hand the other way. So they can be attractive or repulsive. There is so this is the spring. So yeah, the spring, you can either, if I stretch it, what the spring does to me, so if I stretch the spring wants to pull me this way. And if this is the natural position called of the spring. We'll talk about springs more. But if I compress the spring, I push it, I compress it, what does the spring try to do to me? So I've compressed it, so the spring tries to push me this way. It always tries to come back to its natural position. So that's a spring. Okay, what else? What else? You got the force of tension. Tension is when you have a rope or a string. So here is I would show you a rope in a moment, but it's just a string. It's called the tension. Tension force. And it has the symbol capital T. The tension force always, if you have a string, let me just get it. Here is a string. This string. I can pull on this string, and the string will pull on me. For example, if I hang something here, the string will pull on it upward. Or if I pull on the string upward, the string will always pull me down. It always acts along the string itself, or the rope, or the cable, or the cord, different names for force of tension. It never pushes. You cannot use a string to push. I cannot push this thing here with a string. I can only use it to pull. So strings only pull. Come back to this in a moment. The force of tension, let's see here. It always pulls. It's contact. You have to be touching the string. Always pulls. And then there is the normal force. It has the symbol N, little n. Our book chooses little n with an N. And it is, so what is the normal force? The normal force is a contact force. So if I push on this board, the board will push back on me, and it's a force that's always perpendicular to the surface. As I stand on the ground, the gravity is trying to pull me down, but the ground will push me up. That's called the normal force. And the normal force is always perpendicular to that surface. So if the surface is this way, and I put a mass here, I put an object there, the normal force would always be perpendicular. It's always at 90 degrees to the surface itself. All right. It always pushes away, and then it's always perpendicular to the surface. Always acts perpendicular to the surface, and it's of course a contact. It's a contact force. And then instead of listing all of them, you got the force of static friction and the force of kinetic friction. I will talk about them also. They're contact forces. There is the force of friction. It's a contact force. And then there is the drag force, the force of drag. If I drop this piece of paper, because of the air resistance, there is a force this way, resists the motion. As you drive in your car, let's say if you're going this way, the air resistance will be the other way, always opposes the motion. Similar to friction also. There is the electric and magnetic forces, and then there is the force of thrust. So if you propel, like if you have a balloon, for example, and you let the air out, the air comes this way, and then you get thrust. It's being pushed the other way. Okay, so that is that. So let me try to show you just the spring and the strain here. All right, so I hope you can see it. Here is a string, and I can hang a mass on the string. And the Earth is, let's consider the mass here. The Earth wants to pull the mass down, but why isn't the mass falling? The reason is because there is a different force, and it's upward, and it is because it's connected to this string, and it's called the force of tension. That's the force. Now, what keeps the string bound together? Why doesn't the spring break away? Where does the force come from? Well, it comes from the microscopic, interactions within the rope or the string itself. Because after all, it's not a secret, the rope or the string is made of atoms. And those atoms, they have electrical forces between them. The electrical forces can be attractive or repulsive. Okay? So as you try to pull the string this way, the electrical forces will keep the string together, and so they're attracting each other that way. So you can model it as like made of many springs. As you expand those springs, the springs wants to go back closer together. So that is that. Now here is a spring. Again, springs, by the way, our strings are usually ideal, which means they cannot get longer. They keep the same length, and they are massless. Okay, they are massless. And here's our spring. And springs, they're also ideal. Obviously, this spring here has a mass, but we would consider the springs to be ideal, meaning they are massless, meaning their mass is too small compared to everything else that we are considering. So an ideal spring is actually a massless spring here. And you always have to tether or tie the spring on one end. One end has to be tied in order to apply a force to it. You cannot stretch or compress the spring by just pulling it this way. You can't. You have to hold it from the other end. So it's always understood that it's always tied from one end. So here is the mass, and this mass will be tied, will be hang on the spring here. And so the spring stretches and stretches. It stretches enough. The mass wants to fall down because gravity is pulling it. The reason it doesn't fall down is because there is a different force, a counter force, which is the spring force in this case, and it's pulling, it's attracting the mass, it's trying to pull it upward. Why? Because the spring is stretched. And if I pull the mass down and let it go, it will oscillate. The combination of basically these two forces will cause this simple, what we call simple harmonic motion, which we will consider around, I think, chapter 15 or 16 of this book. Okay. So that's when we do oscillations. So that is that. And then I mentioned the normal force. Let me show here. For the normal force, so here's a table. The normal force between my hand and the table right now is 0. There is no normal force because there is no contact. Now, as I lean on the table, there will be some normal force. And if I lean harder, there is even more normal force. And the normal force is, there is no formula for it. How much is the normal force? Well, it's as much as it needs to be so that my hand does not go through the table and it can keep me this way. Now, obviously, if I put enough weight on the table will collapse, will break. I can put a ton and then it probably will break, or 2 tons, whatever. There is some break point. We're not considering that point. We will just consider the table or the surface, whatever it is, the ramp, to be strong enough that it will keep my hand from going through it. The same thing with the wall. If I lean against the wall, then the wall will do what it needs to do to keep me from penetrating or going into the wall. So I push against the wall this way, the wall will push back on me, and that's called the normal force, and it's always perpendicular to the surface. Okay? And actually the camera was leaning downward. I don't know if you saw me pushing against the wall or not. Yeah. Okay. So that is that. And the normal force is also, microscopically, it comes from the electrical interactions between the atoms that make the table, and my hand also. So as I push the table, you can think of the electrons from my hand and the electrons from the table repelling one another, or in addition to that, when you push against the table itself will actually get smaller. It will collapse a little bit. And that, when it collapses a little bit, the atoms in the table, they get closer to each other, but there will be repulsive forces, so they will push away. So that is the origin of the normal force. All right, so let us talk briefly now about Newton's laws, and then basically the bulk will be in applying those Newton's laws. That's what we want to do. So talked about these. So Newton's laws. Let me just write the first law here, and then we continue. So you already know, because this is your second physics class. Newton's laws, there are 3 of them. The first one is the law of inertia, or Newton's first law. So Newton's first law, it says, in the absence of forces, or a body will remain at rest, or in motion at constant speed along a straight line, meaning at constant velocity. It will just continue doing that forever, if and only if the net force acting on it is 0. So if the net force is 0, an object will continue moving at constant velocity, including that maybe that constant velocity could be 0, meaning at rest. So if the net force is 0, it will just continue going at constant velocity. Also, so 0 force implies constant velocity. The implication goes the other way, because we said if and only if. So if the velocity of an object is constant, meaning it's either at rest or it's moving at constant speed in a straight line, then the force is 0. So you can figure out if the force is 0, the velocity is constant, or the other way also. If the velocity is constant, the force is 0. The force is also implied to be 0. So that's the Newton's first law. However, there is one caveat. Newton's laws only apply in inertial frames of reference. Okay? So here is an inertial frame of reference is, so when we set our coordinates, so here's our coordinate system. So let's say I'm an observer. I'm standing here. Right? I'm standing here. And then you're in your car, or or here is your car, right? And here is your car seat. This is the seat of your car. This is your steering wheel, all right? And you're sitting here. And let's say there is a passenger behind you, and they have a cup of coffee here. And there is a cup of coffee here on some table. And so this is the car. So I'm looking at you. I'm at rest. You're at rest. Nothing is going on. The force, so let's say the cup of coffee is sitting on a frictionless surface. Okay? The cup of coffee is sitting on a frictionless surface. So what that means is there is no friction. We'll get to friction, but in short, friction acts always parallel to the surface. So there are only two forces on the cup of coffee. There is the force of gravity downward, and then the reason the cup of coffee doesn't fall through the table is because there is the normal force of the table. Remember, normal force is the symbol little n, and then there is the force of gravity downward. Right? Force of gravity downward. For you, you're maybe leaning on your seat, so there is normal force from the back of the seat here pushing you. There is a normal force from the seat itself, and there is the force of gravity and so on. So that's that. So now, what you do is you start to accelerate your car. So what happens is you accelerate, you stay in your seat. So according to you, relative to the car, you didn't move at all. You're moving with the car. However, this cup of coffee will fall to the back. So the cup of coffee seems to have accelerated relative to you. The cup of coffee looks like it has accelerated relative to you. But Newton's first law says if the net force is zero, the acceleration should be zero. And the net force on this cup of coffee, there are forces in the vertical direction and they cancel, they're equal to zero. And horizontally, we said it's frictionless. So there is no force horizontally, but the cup of coffee seems to have accelerated backward for no reason. So you think, well, Newton's first law didn't apply, or maybe there is a new force. And the answer is there isn't, because remember, the forces are either the forces that you have in contact, or the only force here that can reach out and pull you down from a distance, from long range, is the force of gravity. So where did this, in quotes, force on the cup of coffee come from? And the answer is, there is none. The reason it feels that the cup of coffee has accelerated backward is because you are in a non-inertial frame where Newton's laws do not apply. Because for you as a person here, you're accelerating, you're in a frame that is accelerating. However, to the observer here, the observer will look and say, wait a minute. Actually, to the observer, as the car accelerates, the cup of coffee will just remain. It's the back of the car that's catching up to the cup of coffee. So it is the back of the car. So if the cup of coffee was aligned to you, so let me draw the picture a little bit later, at a little later time. So you're here, this is your seat. And then the cup of coffee is here. It has fell. But you're here. Relative to the cup of coffee, you haven't moved, and the cup of coffee has not moved at all. It's the back of the car that has caught up to the cup of coffee. So you are, as an observer, you're in an inertial frame of reference. Your frame of reference is inertial, and therefore you say, actually, the cup of coffee did not accelerate at all. It's the back of the car that caught up to the cup of coffee. And I know it hasn't accelerated because, well, it hasn't moved. Relative to me, it is still in the same x position, in the same position relative to me. It has not moved as expected, because Newton's first law says it will, if it's at rest, it will remain at rest unless a force acts on it, in which case there isn't. Now, why did the car accelerate? That's easy to explain to you, for you. So here are the wheels. The car accelerates because there is an external force on the car. There is friction between the tires of the car and the road. So the road will push the car this way. The tires will push on the road backward, and so the road pushes on the tires forward, and therefore the car moves forward. And so for you, you can explain everything in terms of Newton's laws. For the person here, will think that the cup of coffee has accelerated backward for no reason, and the reason for that, the explanation for that is because the car is a non-inertial frame of reference. Once the car accelerates and it settles down and it moves, let's say, at 80 miles an hour, then it will just become an inertial frame of reference. If it's moving at constant velocity, then it is a frame of reference itself. If it's not moving at constant velocity, then that frame of reference is a non-inertial frame of reference. I hope that's clear. We'll not dwell on this because the frames of reference that we will be considering all of this semester will be inertial frames of reference. They will be inertial. But this is just a conceptual one. By the way, Newton's first law was discovered by Galileo. So it's really, Newton wasn't the first person to discover it, but he was the first person to list them as three laws. Okay? What's remarkable about this is people for many, many years, let me make sure the timer is okay. Yes, I'm okay. So I can still talk for a few minutes. So for many, many years or centuries, thought to keep an object going at constant velocity, you needed a force. Galileo came and Newton listed it, saying, actually, you do not need a force. In fact, you should not have a force, because if you have a force, the object will accelerate. And so people thought, sure, if something is at rest, there is no argument there. You don't need a force to keep it at rest. Okay, fine. However, if an object is moving at constant velocity, for centuries, people thought, well, to move at constant velocity, you need somebody to be constantly pushing you. And the answer to that, and that's actually wrong, because, and the reason they thought that was because when something is moving in everyday life, there are there are drag forces, resistive forces, frictional forces, and so on. And they're opposing the motion. So for you to push it forward, you're just trying to counter those forces. And so you got to force backward, force forward. You're trying to make the net force zero. You're trying to make the net force zero in order for the object to continue moving at constant velocity. So that's what's remarkable about this. And it wasn't discovered until a few centuries ago, only because people could not, because of the frictional forces. You don't see it in everyday life, where if I pushed a piece of chalk along the table, it will move a little bit and then it stops. So people thought, well, it stops because you actually need the force to keep it moving. Newton and Galileo came along and said, no, actually no, because in the absence of friction and everything and all these resistive forces, if the piece of chalk is moving at 10 meters per second, it will continue forever and ever and ever moving at 10 meters per second, okay, along a straight line. So that is that. And now I want to talk about Newton's second law, Newton's third law, briefly, and then we will move on to basically the next chapter.